Here's one more example of a problem that involves conservation of energy and conservation of momentum. There's a collision. So read through this, press pause, and try to set it up and do as much as you can on your own, and then press play and go through it with me. So I'm going to kind of have the same type of events I had before. My first event is going to be when mass A is on the top here before it starts sliding down, because I know a lot about what's happening there. My final event is going to be when mass A comes back and reaches its maximum height after hitting mass B. And then because there's a collision, I need to have an event before and after my collision. The difference between this problem and the previous two is that in this case the collision is perfectly elastic. Okay, so when you're told that there's a collision, and if the problem describes something like in the previous problems where it's clear that two objects are coming together and moving as one after the collision, or if it's clear that it's a reverse inelastic collision, like the two objects start together and then they separate, then you don't need to be told specifically that it is an inelastic collision. It's just obvious based on the description. However, you do have to be told the problem that the collision is perfectly elastic, or that you have to be told it's an elastic collision, as you are in this problem. You cannot just assume that a collision is perfectly elastic. Okay, so this is an elastic collision. That means both both momentum and kinetic energy are going to be conserved, and I'm going to use that long equation that relates what the velocities are after the collision in order to figure out these velocities here. So let's start with looking at what's happening at my zero event. My total mechanical energy is just K0 plus U0. That's going to be the kinetic energy of mass A plus the potential energy of mass A. It's starting from rest, so it has no initial kinetic energy. And here is the potential energy, so that's 392 joules of total mechanical energy. Now I'm going to figure out how fast object A is going right before it hits object B using conservation of energy. So my total mechanical energy right at the bottom, right before they make contact, I'll call that K1 plus U1. There's the kinetic energy right before they make contact. Here's the potential energy. And the Y position at this event is 0. So the potential energy there is 0. And now I can equate this mechanical energy with this mechanical energy to figure out the speed of the block A right before the collision. And I find that it's going 12.5 meters per second. That's right before the collision. Now, I'm not going to bother going through and figuring out, what's the momentum right before the collision and so on, because these equations here that we saw when we were looking at perfectly elastic collisions, these equations were derived from the conservation of momentum and conservation of energy. So I can just go straight to using these equations where I have the two masses, I have the speed of mass 1 right before the collision, here's the speed of mass 2 right before the collision, and then here I'm looking at it for object 2, or let's call it object B. Here's my two masses. This is the velocity of object B right before the collision, and this is the velocity of object A right before the collision. So when I use this equation here, these two equations, it is already taking into account that momentum is conserved going from this event to this event. And it just lets me skip straight ahead to figure out the velocity of this object right after the collision and the velocity of object B right after the collision. So this already answers the second question here. How fast is B moving after the collision? 8.35 meters per second is moving to the right. A is going to rebound and move with a velocity of minus 4.17 meters per second. That means the minus means it's going back to the left, and it's going to slide up the hill. So now when I want to calculate how high mass A reaches, I'm going to say that when it's at this height down here, it has a speed of 4.17 meters per second. That can let me calculate how much kinetic energy it has. And as it slides up, that kinetic energy will be converted into potential energy until it reaches that maximum height. So I'm just looking at the kinetic energy of mass A. That's all I'm looking at here. and I'm looking at how much kinetic energy mass A has right after the collision, so I use that velocity, and I get 43.5 joules. That's the total mechanical energy of mass A right after the collision. And now I want to consider how much mechanical energy mass A has when it reaches its maximum height, when its kinetic energy at that event is going to be 0, and that's going to let me calculate that height there. So I set this energy equal to this energy, and I find that height there.